Okay, so now that we've established some important computing techniques for probability, let's talk about how these can be applied in the context of analyzing the game of craps, which we've already discussed a little bit. We discussed how to analyze dice, and let's take this a little bit further. Okay, so what are the rules of craps for those who have never played craps? You have two dice. And so it's the game of craps actually a little bit complex because it's not just every roll being independent. There's some dependency, and here's how it works. There's an initial roll called a come out roll. Okay, so in the initial roll, there's a come out roll. And I'm actually going to simplify the game because there's quite a few things you can do, but we're going to assume that there's a bet on the pass line, that we're betting on the pass line, okay, which is a pretty standard bet. Okay, but here's how it works: is on the first roll, it's called the come out roll. So on the come out roll, you lose, called crapping out, if we roll craps. Total of 2, 3, or 12. This is called craps. We win if we roll 7 or 11, called yo 11. Okay, 7 or 11, we win. Otherwise, we enter into a second stage of the game. So the game ends on the initial come out roll if we either roll crap 7 or 11. Otherwise, the roll total, which the possibilities are 4, 5, 6, 8, 9, 10, becomes what's called the point. And then we continue rolling until either we hit the point before, well, we hit the point, in which case we win, or we roll a roll of 7, in which case we lose. Anything else, we keep rolling. So the question is, what's the probability that we win? And then, okay, let's say we roll the point, then that's the end of the game. We can start over, play a new game. Okay, so let me just try to illustrate this for you. Let's consider rolling in succession. Okay, so few scenarios. So let's consider illustrating how this would work and what the result would be. Okay, so roll number 1, 2, 3, 4, whatever. So let's suppose that we were to roll on the come out roll a 5, and then a sequence of rolls as follows. Okay, 5. So what's happened here is on the come out roll, we've rolled a 5. So then what happens is we then continue to roll until either a 5 is the point, or a 7. We ignore everything else. So everything else gets ignored until the next 5 or 7. Okay. And in this case, a 5. So this would be a win. Okay. In another situation, let's say we started with a 5, a 7. No, let's started with an 8 this time. So the point is 8. And we roll an 8. So 8 becomes the point. But in this case, we actually hit a 7 before the 8. So we ignore everything except for a 7 and an 8. We hit a 7 next, it's a law. Okay, and then another scenario would be that we roll a 7 on the first. On the initial roll, that's a win. Okay, so a 7 on the initial roll is a win. A 7 after the point is established is a loss. It's just how it works. And just to give one more example, a 2, snake eyes, on the first roll, that's a loss. Okay. So we want to calculate the probability that we win at craps. And how are we going to do this? So what's the probability that we win at craps? Win being, it's a pass line win. Strategy. So this is the question. And the approach is going to be that we condition on the come out roll. So a common approach, there really are only so many things we can do with probability. Probability axioms are pretty limited, but probability is a pretty powerful framework. But a common thing that we're going to see over and over and over again is we're going to condition on the first roll, and we're going to apply the law of total probability. We will use this technique constantly. Okay, so this is something that is just so widely applied in probability. So this will be one application of it, but it's like the go-to strategy in a lot of problems involving probability. So remember this approach. Master this approach. Extremely important. Okay, so how are we going to do that? So first, let's let W be the event that we're interested in. So W is the event that we win. And notice that it's actually hard to write what that event is in explicit format because it's a pretty complex game, right? Because we could roll indefinitely long. You could roll, a given game could last hundreds of rolls, theoretically. Very rare, but it does happen from time to time. Or it could last one roll. So there's so many possibilities that could cause us, that could be in this set. So we have to account for them all. And how are we going to do that? Okay. So let's let W be the event that we win. And let's, going back to notation we've used before, let's let TI be the event that the first roll has a total of I. And this is, of course, for I from 2, 3, up to 12. Okay. So the events, notice that the events T2, T3, T12 are mutually exclusive and exhaustive. So if I roll a 6, in other words, T6 occurs, none of the others can occur. It's just not possible. And the only possibilities are 2 through 12. That's just the only possibility. So they're exhaustive. So what does that mean? That just, formally speaking, this means TI intersect TJ is empty for all I not equal to J, and that the union over all TI is the set of all possibilities. So that means that the TIs partition the sample space. And then we can apply the law of cases. Okay. So by the law of cases, or the law of total probability, by the law of total probability, probability that we win is equal to the sum of all overall cases, I from 2 to 12, of the probability. So what is it? Let's look at it here. So in this case, A is going to be the probability that we win. The cases are the TIs. So it's a probability that we win given TI times the probability of TI, right? So those are the equivalents in this case. That's the law of total probability. So the probability that we win given TI times the probability of TI. Let's first recall the probabilities of the come out rolls. We calculated this in a previous class, and I'm just going to copy them down again here. So now the way this worked, to try to make this as quick as possible, is that there are 36 possible outcomes, and we have to count how many possible ways there are to roll each of these numbers. And we've done this already, and it's kind of it's like a pyramid. It's triangle, actually. 1 up to 6, 6 down to 1. Right, so this is a review. Oh, okay. And now what we need to do is we need to actually fill in these conditional probabilities. So we want to fill in the conditional probabilities that we win given each of the cases that we're considering. Okay. So again, we have 2, 3, 4, 5, 6, 7, 8, 12. Now, to start, there's a couple of easy cases, right? Let's start out up here. We first know that we lose if we roll craps on the first roll. So color this is green. So 2, 3, or 12 is craps. If so that means in the event T2, T3, or T12, we lose right away. So the probability we win given those is 0, of course. Similarly, we know that if we roll 7 or 11 on the first roll, we win right away. So those are easy. We win with probability 1 on 7 or 11. Okay, so then the remaining question is, what's probability that we win given that the point is established at 4, suppose, for example? Now this actually turns out to be pretty tricky. And so we have to be a little bit, we have to think a little bit, how are we going to do this? So the first roll was a 4. And now we're pretty much entering a new game. And the game is, okay, 4 is a special number. It's the point. And now what we want to do is we want to roll and we want to see, okay, what's the essentially what we're asking is what's the probability we roll a 4 before we roll the next 7? Okay. So now we have to use what's called a recursion. Okay, so now we're going to condition on the second step. Okay, so for example, assuming the first roll is 4, we can condition on the second roll. Okay, so then we're asking the question, probability that we win given that the first roll is a 4. And what are the two possibilities now? The two possibilities are the second roll. Well, let me write down the law of cases again. So probability that we win given T4 and the second roll is a 4 times the probability that the second roll is a 4 plus probability that we win given T4 and that the second roll is a 7 times the probability that the second roll is a 7. We have to take those two possibilities into account. Those are when the game ends on the second roll. And then finally, probability that we win given T4 and the second roll is not a 4 or a 7 times the probability that the second roll is not 4 or 7. Okay. So what's the first one? Probably that we win given that the second roll is a 4. If the point is a 4, that's 1. Probably that the second roll is a 4 is right here. 3/36. Okay. Plus probability. Let's just follow along here. Plus probability that we win given that the point is a 4, but the second roll is a 7. That's 0. Times the probability the second roll is a 7. It's irrelevant since we're multiplying by 0, but it's 6/36. And then finally, let me actually move this to be a little consistent. And then finally, probability that we win given the point is 4 and that the second roll is neither a 4 or a 7. What is that? That means the game continues and we're basically we're playing again where we try to get a 4 or a 7 on the third roll. So this probability takes a little bit of thought and there's a little bit of an assumption here. But that third roll is going to be like a replicate of the second roll. So it's actually equal to the same as just the probability of W given T4, right? It's as if the second roll never happened. We just ignore it. And then what's the probability that the second roll is not a 4 or a 7? Well, it's just the complement of rolling a 4 and the complement and not rolling a 4 and not rolling a 7. So it's 1 minus probability of rolling a 4 minus probability of rolling a 7 on the second roll. Okay. So this gives us an expression, right? So what this tells us is that the probability of winning given T4 is equal to 3/36 plus 1 minus 9/36, so 27/36 times the probability W given T4. So we have one equation, one unknown. So we solve. Okay, and we solve for this and do a little algebra. What do we get? we get 3 divided by 36 divided by 9 over 36, right? That's 1 minus 27 over 36, which is 9 over 36, which is 3/9, which is 1/3. So we can fill in this probability here is 3/9. And I'll leave it as an exercise to continue on and to calculate these probabilities yourself. But the same technique can be used to get each of these probabilities for each of the points. So now we have the basic ingredients that we need. Okay, so then what's the probability of winning at craps? It's probability that we win given T2 times probability of T2 plus probability that we win given T3, probability of T3, etc. Probability that we win given T12, probability of T12. Let's just copy these tables down. And realize that what we need to do at this point is oh boy, they're not perfectly matched up, but we basically, well, we essentially we need to do is we multiply each case together, right? So we have I, and we're going to multiply probability of Ti times probability of W given Ti. So for 2, 3, and 12, that probability is 0, because we're multiplying everything by 0. For 7, that probability is that product 6 over 36. For 11, it's 2 over 36. Those are multiplying by 1. Okay. For 4, it's 3/9 times 3 over 36, which turns out to be 1 over 36. So that's the same for 10. And then it becomes, let's see, it's 1/9. Check my math here. I think this should be right. And this one's a little not a great number, but 25 over 396. That's right. That's where these are coming from. We add these up. And what do we get? So if we add these up, we're gonna get my number is about 0.493. Okay, which sounds right to me. There's always a possibility of making a little bit of a mistake with the fractions, but sounds right because it's slightly less than 50%. And it has to be because this was calculating the probability of winning on a pass line bet in craps. And the way the pass line bet works is you put up money on this bet, and if you win, you get paid back. You double your money. So if I put it up $100, if I win this game, I'm gonna win $100, and if I lose my $100. In order for the casino to make money on that bet, I need to be winning that bet less than 50% of the time, which we see I'm winning 49.3% of the time. So that is a illustration that, of course, the pass line bet in craps is a negative is a losing bet. That gets us into concepts called concept of expected value, which we haven't talked about yet, and we will talk about in the future. Let's summarize this, though. There was something that we did here that was a little bit out of the blue, which was in setting up this expression right here. We had to make some assumptions because we then had to condition on the second roll, the result of the second roll, not just the first. And there was an additional assumption in there about the independence of the rolls. And so we're going to talk about next independence. What is the definition of independence, and how does that assumption of independence come into play when we're calculating probabilities and conditional probabilities?